we didn't do the usual saying on Slack and things like that. We didn't do the usual announcing it on Slack and things like that.
Oh, right.
Let's look at the people. You're not yet.
Yeah. Oh, okay. Me? Yeah. Okay.
Because that's what he's measuring.
They're very high. You can breathe less. That's your. Yeah.
That's my
breathe
goal.
out less.
Yes.
Breathe in more.
I will try to do that. And if I'm dead, I'll blame my hero.
Next time. Yeah, it could also be fun. Yeah.
Yeah, levels again.
Could be that. Yeah. My girlfriend's parents were there this weekend. Pardon? It does. Yeah. Right. Okay, nice. Right. See. Yeah. Whereabouts?
That's me.
Yes, whereabouts is it? Jeez. Okay, who organised it?
It's just
Oh, nice. That makes sense. It makes sense that you would let him. Around time here on that. Oh, really? Oh, nice. Oh, that's cool. Have fun. Oh, that's excellent. How long are you there for? Okay. You're very for us. The week after, okay. Now it's algebra representation theory. Because they have like bubbles. Yeah, exactly. Yeah.
Two other ones now.
Yeah. The whole program. Good way to do it, sorry. Oh, nice. I see. I posted to kinetic theory, but I feel like almost nobody's here. I usually just, yeah. Quite a few minutes. Is it 5 minutes? The Cambridge 5 minutes is unofficially official. And everything starts at 5 past. What's the time? It's the same. Yeah. No, I don't know if it's true in the UK. I mean, Germany. Yeah, usually it's right on time between Cambridge. In where? Germany, yeah, and the Netherlands and the Nordics. Which must be incredibly confusing. Because I mean 5 minutes is like, oh, you're a bit late. 15 minutes is like you can have a coffee.
But how big is the difference?
Yeah, that's true. That's very true. How does it work in France? How does it work in France? Things start on time, or if the lecture is 11 o'clock, does it start at 5 past?
Maybe, yeah, it's
Yeah. Oops, sorry.
they're on time.
Never on time. People here talk about Jewish mean time. If a Jewish event is supposed to start at 6 o'clock, it starts at 7.
Indian.
Yeah, I'm sure it's very
If you're
similar.
on
Yeah,
time,
exactly.
I think it's rude to arrive on time, something until you do something with the other analogy.
Yeah, that's right.
I get it.
Yeah, it's nice that we come there. Should we get started? So,
Except I'm fine.
Does anyone want to? Okay, so our first speaker today is Jin from Rias, Cambridge, and Texas. Is that Texas Agriculture? Texas A&M, 3 whole universities. It's taught us about the expanding configuration of radiation gaseous stars. Thank you very much. Thanks for the introduction, and it's a great pleasure to stay. I want to expand as my previous place in Berlin, University here, possibly University, Texas A&M. Okay, so today I'm going to talk about the expanding configurations of radiation system, review using how to find what has been done, and then I'll briefly mention this and so let me show you and today we're going to show something quite obvious in the middle. Yeah, so all right, let's review. Let me start with mentioning the hydrodynamic. Here, no is the density, U is the velocity from R3 to R3, and we have the first equation is the security equation. You know, the conservation of mass. The second equation is the conservation of momentum. Okay, Newton's second law to describe the left side transport momentum, and with the viscosity of reaction blue, and with the external forces. Yes.
You might know we're very close. This is super loud, so can you just speak up a little bit?
Oh, okay, sure.
Yeah.
Sure. I mean, okay. The last equation is the conservation of energy, and here is the specific energy, and this transport energy plus the energy transfer between heat and the kinetic energy due to pressure, and the right hand side is due to this two term, this one is due to the viscosity, and then we have law of course, and then we have the heat source. Of course, this equation is compressible. Any compressible. Therefore, I need to finish the equation. I have to impose the equation of state for compression. In particular, I will only take care of the ideal gas, where P is equal to some constant K times theta. Theta is the temperature. The same thing for the internal JE is equal to C nu times theta. C nu is also and we have the viscosity taking the symmetry part of the gradient plus the and in the special case, with divergence is 0 and 3, and you only see the symmetry gradient. And in particular, these two new, one is called the shear viscosity, other one is called bulk viscosity, corresponding to the viscosity caused by cut through the flow, which is the shear viscosity, which you usually see in the compressible flow, and the other one is called by the compression viscosity. And the other one, the bulk viscosity is weaker than dynamic. All right.
And it's a curly F. On the second, for the momentum equation, the last step is gradient of.
Gradient of capital F is a forcing term.
It's a forcing.
Yeah.
And on the last that follow the S, is it the S scalar gradient U? The second blue term?
Second one, yes. This one
Yeah, just
is this one.
The product is just standard scalar product.
Scalar, no, it's a matrix.
It's a matrix.
Tensor. So tensor multiplied with a tensor. Okay. And in particular, we have the entropy divided by S equal to log P over log to the power gamma, which gamma is denoted by 1 plus K plus C. And this is just the law satisfied by the entropy into density. It's just a talk about the entropy today. So next, I will move on to the gaseous star. This is the equilibrium state of the isotopic flow. On the left, on this equation, you can see here on the left-hand side is the pressure. And we don't have the namely, okay, under this law, if the S is constant, then P is equal to log to the power. So therefore, in here case, we have this pressure is log to the power gamma. In the right-hand side is the cell gravitation itself. In particular, the phi, the Newtonian gravity potential is given by the Newtonian equation. Okay, and also in case that the density does not occupy the domain of free spaces, the first equation will be true inside. And the second equation is the equation three, meaning that the second equation is solve. And if you divide the first equation with flow and take the diversion, for the simplify the two equations, one level equations. However, this equation only holds true inside, outside the flow. And here is a briefly summary of the existence theory for this equation. So for gamma between 1 and 6 over 5, you have there's no solution for this equation. It's well known for the mathematical equations. And for gamma is equal to 6 over 5, that it exists at ground state, meaning that the solution is spread out. And there's no free boundary. There's no boundary separate the flow from the vacuum. And when gamma is between 6 over 5 and 4 over 3, we have one ground state equation, which is the same as 6 over 5, and we have one singular equation concentrated at the center, which is and parallel support, and one space smooth inside. That's when gamma between 6 over 5 and 3. And in the case of gamma equal to 4 over 3, there depending how many mass you have, how much mass you have for the density, then the integral of log depends on the number. If the number equal to the great number, then you have only one solution, and that one solution can be scaled up and down. There is a scaling property, which I will mention it later. And if the mass is not equal to mass, then you have no solution at all. Because given this solution here, given this equation, you have to complemented with the deterministic solving condition. In this case, a total mass. And when gamma is bigger than 3 to 2, we have exactly one solution. Okay. And this fluid mechanic description of gaseous star is, as far as I can tell, starting to just Seca. This is referred to this book where he introduced the model starting from the basis and stuff like that to divide the closure, which is eventually led to this fluid dynamic description of gaseous star. And in the paper by Liu and Yao, although they are not really studying this model, but they mentioned that using the monotonic inequality and the variation structure of the solutions, you can prove that the solution have to be zero, which is obvious to us. Take time to solve it. And for rotational gaseous star, namely this is not this equation. We have zero velocity. Gaseous star. The existence theory was put by Beals, and later on by Kapladi and Redman and other people, they proved the configurations, like how many ring we have and the regularity. But I have to say, aside from finite ring, much important. That's for the rotation gases now. And remarkably, when we return back to this non-rotation gaseous star.
So when you say finite ring, are they planar rings or shells? What do you mean?
It means that the configuration gas like this.
So it's planar.
It's well, it's concentrated.
Yeah.
And then it's like finite number of isolated mass.
But it has a volume, right? It's that thickness.
The thing is, we don't.
Oh.
We know the finite number.
As in, you don't know whether those rings have height or not.
Yeah, well, I think they have here's how they eventually put the ring bundles.
Right.
Very
So they're not okay. So they're not completely planar.
not completely.
I see. But they have no velocity or anything inside the.
No, they only have rotation. Okay. A remarkable feature about this configuration for the non-rotation star is that it says by the so-called physical vacuum. And what it meant, physical vacuum, it implied that the Friedrich symmetrization method for hyperbolic system. If you want to put local levels, for example, and that precisely means only out by Xin Liu in 1996 that the sound speed is open across the vacuum. So with more precisely, you have gradient. This is a square of sound speed. It's extreme, like strictly crossing the vacuum. Okay, so in other words, characteristic approaching the boundary equal bounce back to know what so that's the physical vacuum of this solutions. Okay, so this is another picture of gaseous stuff, and you can see that like this last CMS, and it's a very complicated model. And what we want to see is to generalize how we generalize the isotopic. Obviously, we want to capture the energy generation of the gaseous star and want to capture the radiation diffusions. And radiated diffusion of the gaseous star will be activity. And last one is we see what we can let me going back to the isotopic. This is an applied estimate for the isotopic. And we are solving the Euler equations. This graph, isotopic. So this problem is very difficult. It was pointed out in 1996 that the difficulty, and it's solved like after I don't know 20 years later. Okay. By John and Masmoudi and okay. And I'll briefly mention not how the structure of the so passing the equation into Lagrange equation, if you track the particle path, you can briefly write the equation of this problem. It's like a wave equation with the generate coefficients. Remember, rho will approach 0. And on the right hand side is another.
So subscripts here are derivatives.
Subscript is derivative, yes. And low 0 is fixed because we already passed it to x. That's okay. So first step is doing the tangential estimate. Eta is the Lagrangian flow measure.
Oh.
Yeah. Do I need to? It's okay. Yeah. Eta is a Lagrangian flow. So yeah. Before that is a two equations. One wave equations. So first doing the tangential estimate. So there's only one space variable. The only tangential variable direction is the tangential time, the space time. So it's the time derivative. Because time derivative doesn't change the boundary condition, you can easily get out to estimate the end for this time function. And then you try to do elliptic estimate. Normal direction.
Here you have your one problem, but the boundary is fixed now.
Yeah, because I pass it to
Lagrange.
Because I pass it to Lagrange.
And why the subscript 0 on the row?
Because yeah, the same reason, because you pass it to that.
Okay, so just mean the same row but in different set of coordinates.
Yeah, same law. Yeah, in the original law is like log 0, it has to max. And then after you're doing the tangential estimate to the equations to recover the spatial derivative from the time derivative. So coming from these equations, you can move the spatial derivative on the left side and the time derivative on the right hand side. When you apply space derivative, say 2 partial x to the power 2 plus L, and to the equations of course to the partial x to the power L, and then you get this identity. And then you manage the number, counting the number a little bit, then you can realize when you pass one term derivative, or it says when you pass 2 term derivative to one space derivative, right? That's then the price you pay is that you have to add 2 times the sound speed. That's the weight. So this is the energy structure. In short, if I denote omega as a distance to the boundary, which is the square of the sound speed, then you can, from the previous slide, you can get the energy of this time. So it's like this 1-to-1, one space to one time, you gain one weight. Yeah, two extremes. Okay. So yes, alpha is 1 over gamma dimensions. And then we try to do close the estimate using the value. For example, if you're starting with the infinity norm of partial x t, this is exactly the divergence. Okay, the infinity norm, because now we are using one dimension, is one. Okay? And using Hardy inequality, where it tells you that whenever you have one more derivative, you get 2. Because you have 2. And then you keep doing that, in the end, you get something like that, doing L terms. And we want this one to be bounded by our energy, right? Or K level energy. It's here. So these have to satisfy two constraints. One is that total derivative is equal to K, which is 2 plus L is a spatial derivative in one term. So get 1 plus 2 plus K L. Another one is that the weight is less than the bounded by the weight. So what you get is 2L have to be bigger than alpha plus K minus. And solving this system equation, you get K have to be larger than 5. If you want this system 1. Okay, so that means that if the it could be low, kind of very low, but this is at least it's permissible. All right, so this is just a prior estimate, the very simple versions. Even the one-dimensional version is more complicated. This one, let's skip another.
Sorry, is there a prior estimate in the sense that any solution, for example, these mixed derivatives will be controlled by the energy? But do you know a priori that the energy is controlled?
Applied in the sense I didn't show you how to construct it. How to construct these solutions.
But any solution, the energy will be finite.
Yes,
in this admissible range.
Exactly. You assume that it's any solution. So the actual conjunction is not. Because you have to deal with the degeneracy.
Right.
And if you take the parabolic approximation to the degeneracy.
Can I ask you one thing?
Yes.
If you want to construct solutions, so the rho not verify an equation itself, or is just the weight here? It's your weight omega is linked to rho. And rho is part of the unknown, or because also you really think of it as a coordinate.
I think of it as a coefficient.
As a coefficient.
Yeah, because the whole point of passing to Lagrangian coordinate is that the density can be represented by initial data multiplied with the divergence, divided with the divergence. Divergence U is represented by. So reducing that.
So the difficulty is not for the construction of solutions. It's not like if you want to try to make like a fixed point argument or iteration. Let's say I'm trying to understand why is it so difficult to to go from the arbitrary estimates to the construction of the solution?
But because of the generalists, you don't really have that much clarity when you're approaching the model. And you have to construct a elliptic approximations that is like captive to that approaching. If that makes sense.
So at the end of the day, for the solution that you prove that exists, in what space does it have?
Well, it's just like that. It's one. One. Yeah. At the end of the day. But its construction is done by John small people. It's not done. So, okay, so that's the local web estimate if you want. And then I would mention a little bit about long term. Go beyond those. So for gamma smaller than 4.3, provided the bigger than 6.5 solution, choose a solution with common support. The solution are not stable. The equilibrium are not stable. Then we have small deviation go very bad. And when gamma bigger than 6.5 is stable, but only for viscous flow. Because originally it's in basic flow, dissipation. You need to have dissipation to get the stability, the asymptotes. And here is a brief review of the literature. For viscous flow is proved by John and Tice. They prove the instability with viscosity in that action. And the stable stability result is proved by Journey to paper showing that with viscosity we stabilize the get isotopic stability. In the investor case, a linear study was done by Song-San-Ling, and the conditional stability was proved by 2003. The conditional is in the sense that assume the solution globally exists and it satisfies energy inequality. So you have to assume that this condition. And John studied the instability. But this instability is not the same as the instability is like instability. It says that it have a growth mode. And the small perturbation will go beyond the states. We don't know what happened. Will it fall back to the state or not? Okay, so this is instability. And now I will focus on gamma equal to 4.3. And this is called the radiational gaseous the critical case. Okay. And in the isotopic model that exists for mass, namely that it is only for gamma equal to 4.3, there's only one total mass that you can construct equilibrium states. When the mass is bigger than this total mass, then the gravity is too strong. There's no equilibrium, but you can construct collapsing. Gravity is too strong to get together. And when the mass is smaller than the mass, then the gravity is weaker, flowing out. There's no equilibrium, but expanding. And this is proved by the 8. Okay? And the stability results proved by Hansing and John in 2017, where they also the oil equation as well for the expanding equations. Okay. And really, our focus, this kind of phenomenon was presented by the subsequent the following slides. And let me recall the equations. In isotopic case, it's first in radial symmetry equations. Then we have continuity equation and the pressure itself. Okay. So the self-similar answer is that for any given y between 0 and fixed number 0, you can see R0 is like Lagrangian point, and you choose R equal to R some alpha. Alpha is basically separation point, alpha t, and times y. And the density low, scaled it like this. This is basically because this is the scaling that you have the conservation of x. Any alpha, this under the scaling, the total density of low is the same as the total density of y. And then we scale the velocity by using that. And you plug into the equation, then it will reduce to this following equations. Just the only equation for low bar. And the whole point to choosing that is something minus is related to the signal. And this is a Lemaitre type equations. Okay? Compared to before, additional term is the 3/4. And additionally, we have the other, because it's basically a separation variable, space, E, and the time. And then you solve in this term of the E. For delta smaller than 0, there exists a escape mesh, escape velocity, that the alpha 0 equal, if the alpha 1, which is the initial data time of alpha, you get the alpha t equal to x. And this solution, we call it self-similar expanding because A is expanding and B is not. Namely, the asymptotically is expanding in the rate of t to the power 3. And then the other one is the linear escaping configuration. The same when delta is smaller than 0. If the initial velocity is bigger than the escaping speed, then it will expand out. The self-similar solution will expand out. Or the delta is initially is not will also expand out. You get a solution asymptotically behaving like A. And the final case, if the delta is smaller than 0 and the initial velocity is smaller than the escape speed, then it will collapse. The alpha 1 star basically the first escaping velocity. Okay, so we were focusing on these two types of expanding configurations. And I will say it now. This self-similar expanding configuration is a very popular style in the physics community because it's explicit. However, I would say it's not stable. So I will pass to Lagrangian coordinate, but now it's symmetry. I have to choose a coordinate. So the coordinate I choose is the following. I calculate for a radius. I calculate the total mass inside this radius, and I find the alpha, which is the self-similar solution, if you want, such that the total mass inside this alpha is the same as our motivations. And then we match this one to the low bar, which is the mass. And this is exactly what I mean by this Lagrangian. And you take the time derivative and space derivative, these long equations, you will recover this continuity equation, which is exactly the flow map. And the other one is the density representation in terms of low bar and this R. Now R is our Lagrangian by the eta. After I passing this, and then I study the perturbation variable eta, the perturbation is our alpha, which is our expanding configurations. When it's 1, then it's the same. So I study perturbation, then it's and this is very important. Instead of R minus R alpha, I choose R over R alpha, because this would get me a homogeneous in this basis, not dependent. And substitute this perturbation variable into our equations, our online equation respectively, and you end up with this massive equations. And these two terms given by the acceleration thing, if you want, and then this one is given by the pressure and subgravity. And so out the leading order, you get this one. And this is the last one is given by pressure. So these are massive equations. And the worst thing is that delta we don't have a specific sign. But delta smaller than 0, we don't both only sign. Okay. And it's very difficult, but and we have a damping term for eta t as well. But this is caused by the experiment. If you don't exactly experiment, which you don't see this. It's only a weight condition. Next, I will do a change of time variable. The whole point of doing the change of the time of change, the time variable change of coordinate in time is because I want the coefficients in the damping is the same order as the coefficient. I just change the coding so that alpha to the power 3 is scale like alpha to the power 2. And after I doing this, because our configuration expand different ways, so I have to choose different one. After doing that, our structure looks like that. Looks like the equation. So let me review. One is the damping structure with the weight given by the alpha. And then we have this one is given, and the last one is the delta eta, which is this guy, given by the structure. And using this equation, we remember our delta doesn't can be possible. We don't have a possibility from there. So the theory proved by Patrick and John in 2017 is that suppose eta times 1 is some weight is equal to 1, equal to 0. This is basically energy conservation if you write it back to the original equations. And then we have the spectral gap saying that this this operator is coercive. Okay. All right. So based on this observation, they prove that cell-similar expanding configuration are stable with respect to small population first. And for linear, the cell-similar expanding configuration is the one expand like not linear expand, t to the power 3 that.
This condition, eta scalar 1 is equal to 0. This is on the data.
On the data, on the initial data, and we work with the solution because of the energy conservation. But remember, our energy, our kinetic energy is positive, potential energy given by the pressure is positive, but the potential energy given by the gravity is negative.
And this does not include the delta also here could be negative. So is it do you have
it allows delta to negative. Okay. And for the linear expanding configuration, you need delta bigger than a negative number that should not be too negative. So namely, this one should not be too stronger. This should not be stronger than the coercivity delta.
Can I ask one thing? Yeah, so if you just try to do like the basic energy estimates for the equation of
yeah,
you get a term which will be like delta eta squared, delta negative. This can be maybe absorbed by Hardy.
No. Because you can do it by Hardy, but because we don't have an electric operator on the side, then you pay too much weight, too much spatial derivative. You have nowhere to cover. That's the problem. All right. Okay, so this is the result proved by Hardy and John. And the result basically is saying that the solution under perturbations, their result is proving that the perturbation will lead to a solution derail to another cell perturbations of the same type. Maybe it's a perturbation of cells and similar expanding configurations. It will not asymptotically converge back to the original configuration. It will converge to a phase change in the same as the linear expanding. But this is for the implicit and rely very much on the energy conservation. You can see the energy conservation as a condition for your array. And this is roughly and the all right. So let's. This is the previous result. I'll move on to viscous case. How we see this. So when we put back the viscosity, obviously you have the viscosity here in the momentum equations, and we have additional boundary conditions because of the viscosity. Okay. And we're calling the S is equal by this. It's shear viscosity plus bound viscosity. And in the case of mu bigger than 0, namely we have shear viscosity, but the bound viscosity is equal to 0. In this case, the previous cell similar configuration is still the configuration for viscous, because in this case, both the viscous tensor and this boundary condition doesn't do anything to the cell similar expand configurations. Okay. And for these two, we have both these two configurations. The result we prove is that the cell similar expanding and the configuration expanding like 2 to the power 2/3 is unstable. In the inviscid case, it's stable. In viscous, it's not stable. And in the linear expanding configuration, still stable. So in a more realistic gaseous style, you probably should see this cell signals expanding. Very stable, expected. That's our result. Okay. All right. To see the unstable region or the cell similar expanding configurations, if I let me start with the homogeneous perturbations. Namely, the perturbation is like in every coordinate, it's like the same rate. So you will end up with a perturbation satisfied by an ODE in time, it doesn't do space. And this is the ODE gap doing this kind of perturbations. And this ODE, we can plug it into the plotted phase space. Horizontal is eta, and then the curve given by the purple is the right-hand side of this ODE, and the curve given by this is blue, something between blue and purple. And that line is the if you multiply this equation correct or transform it into the correct form, you get this second equation. And the second one is a conservation of energy. Maybe this is the tau, it's a coefficient multiplication point. Okay. Right, then obviously you can plot the sign in phase space, and then you can end up with this dynamic. Okay, so obviously you can see that for any perturbation starting away from this blue curve, it will like bound initially because the momentum. You can still go towards the curve, but eventually it will scatter out, so it will stay. And that's the whole point. Okay? And why in this case stable? Because in this case have the energy perturbations. The perturbation basically stay on this group, on the blue curve. And on the blue curve, all the angle is put into zero. That's why in this case is stable. Then you have energy conservation, so stay on this. But when you have viscous perturbation, they will immediately destroy the energy perturbations, so any perturbation will give you away.
So I'm confused. You're saying that this is different from the inviscid in the viscosity case, but on the top you have viscosity had no effect.
No effect. Yes, the only effect here for coming from viscosity is that destroy the energy conservation. In the inviscid case, you need to perturbation stay on this curve, on the energy conservation, so it will still stable. But when you have the viscosity, any perturbations that a large portion of viscosity perturbation will give you this energy no longer conserved. Either it go up or go down, no matter how what it does, it will scatter it out. All right, so this is the homogeneous for these cells. And move on to the linear expanding configurations. We have very similar structure as before, except that we have the viscosity relating to. And now I do the L2 energy state, and aside from this one, the same trouble rate as before, we have additional dissipation given by the viscosity. So this is good and fine. So for delta is smaller than 0, we have using the fundamental zero calculus to control these vectors using this damping and basically using this damping. So in this case, I can give a explicit conditions. It depends on the initial data for expanding configurations. It's coming from the L2 energies. However, if we want to try to do higher order estimates, say time derivative, what we end up with is that the viscosity will give you something back. Because when you give time derivative, when you divide derivative applied to the coefficient, you get an implied term, and it's not precise. But in order to handle this term, the energy estimate, we have to introduce time weight in the energy weight in time. So to control it. Another thing is that unlike the general heat equation, because I only have we only have shear viscosity. mu, the other one is bulk viscosity is 0. So the dissipation is in 1D, you don't see it, but in the reality is that it only gives you the control of this guy. And this guy is simply not good. So we have to make use of the damping to give you the equation as well. But however, this is like 2 different time waves, so you have to really check the time wave. So do that, then while to doing that, you check the number, and this is the energy. And you have the basic L2, and then you have the alpha is the, alpha exponential tau. Then you have like positive tau and negative tau. That is energy, and you have the dissipation, and finally we can have this small dissipation. So basically stable. Okay, so that's the isotropic model based on this. And now I turn to the thermodynamic. I briefly mentioned the CFS. So which means when the thermodynamic model means that I abandon isotropic flow, we really have to deal with the temperature. Okay. Now we have to deal with temperature, aside that is the pressure. And we have to give an equation for the temperature. But temperature is not like gravity. Temperature only exists inside, outside the flow. We don't have temperature. So the Poisson equation for temperature is given by the gravity equation here, and only hold inside the flow. And it's a big equation, of course, I need to give it up. But remember, our domain is unknown. It's part of the solutions. So we really have to tackle this one. And we spend some time to find the variation structure for this one. We did not find it. So how we solve it is like basic reductions. Okay. Our results show that for epsilon k, epsilon is this right-hand side. So here, k is the fluid number. And if epsilon k between 1/6 and 1, there exists infinitely many solutions to this system. And it satisfies the following this whole difficulty for flow and ellipsis for theta across the vacuum. Of course, when we talk about that, it's one-sided. All right. So physically, this epsilon means the heat generation rate. Remember, this is the gas and roughly proportions to this. That's why it's epsilon times. For simplicity, I let it to be a constant. In reality, we just set as both. It's very depends on density and stuff. Okay. All right, so this is the result in the equations. So how we prove the existence theory is that we observe that for a solution exists, we have the self-gravity have to be parallel to the normal direction of the surface. So then we want, if you have a configuration, no matter what it looks like on the surface, the gravity has to point downwards. Okay, on the surface of the star, the gravity has to point downwards, normal directions. And under this observation, we have the theta plus, well, actually the psi is constant along the ground. And theta itself obviously is constant, because it's yellow. And then you have this combination is constant. And because theta and phi both satisfy everyday equations, although the domain of solution are different, but certainly in the cross section, the same domain inside the flow is satisfied the same everyday equations. Then you get a harmonic equation for this combination inside it. And because it's constant, you can use maximum principle. That means the theta plus epsilon phi have to be constant all along, only in the boundary. So constant inside the flow as well. And therefore, we take the derivative, you get the gradient, theta gradient phi, satisfy these relations. And you plug in back into the momentum equation, pressure gravity balance equation, we eliminate the self-gravity. You get a relation between theta and flow. You get the theta can be represented by a function flow with a freely choose constant phi. And this C precisely accounted for why we infinitely solutions. And plug that into original equation, it leads to the equation inside the isotropic flow. Then I can use the isotropic model to solve the equations. And this is the previous isotropic model. So this is like a gamma. All right, so this condition precisely is gamma because it's right. So with that, I can have the equilibrium existency, and we have the regularity. So next I will mention, okay, so physically remark. So epsilon k, k is a constant for any gas. Epsilon representing the heat generation. So the remark so for epsilon k between 1/6 and 1 is reduced, the existence will be reducing the regularity. For the non-existent result, outside this interval using Boyas type argument, we can directly prove it. And the physical interpolation is that when epsilon k is greater than 1, that means they have too much heat generation. Then you have like the pressure generated by the heat is too big, and the gravity is not enough to hold it. So you don't have you don't have balance. And for epsilon k smaller than 1/6, I mean this heat generation is too small, it ends up with just too smaller pressure, and then the gravity is overwhelming the pressure, and it should be collapsed. We haven't found ourselves in a solution to that. But nevertheless, it's a physical interpretation. And let me return to our key observation, and be the gravity have to put it downwards. How we see this is that you can rewrite the gravity and tensor balance equation. If you formally divide it by no, even though the first term here you divide it by 0 on the boundary, doesn't make sense. But if your solution exists, since to the regularity probability equations, you have gradient theta gradient phi. Regularity. So you can talk about this quantity across the boundary. And then you discuss the levels to find out that this one have to be parallel to the surface, the tangential direction of the surface, and exactly down this. The red curve is the level set, supposedly, and when you're approaching the boundary, because it's regular, so the level set should not go too much change. And if it's not parallel to the level set is not parallel to the surface, then you will end up with some changes. So briefly prove back to that geometry. Okay. Now we have some similar solutions, and we have a solution for the equilibrium states. I observed that we have this Celsius structure, and we scale the same for density, but the temperature scale is not dictated by equations. And you scale the domain for any in the S, you can get another solutions. And you can construct a one map of this S to our previous C, also C, 3D variable. And with that, you can this is another explanation why we have so many solutions. And in particular, you can explain the internal the density and the center temperature are related to how big the radius of this gaseous stuff. Moreover, if you choose S to depend on time, then you can construct an expanding or collapsing configurations. For Xin Liu equal to 3K. So that's for the equilibrium and the consequences of the equilibrium states. And then we studied the local wave closeness for the full equations, the evolution of equations. From the South China. Okay. So now we will, and then we look into the stability result for the the expanding configurations. Really, it was inspired by that study. And we have this similar answer for the density R, but for the temperature we have the dictated by the Celsius structure. And the perturbation variable again we have the exact just like before, but the perturbation for the density for the temperature is given by this. But for the same reason, we wanted to have a good separation. And our result is saying the same thing when we only have shear viscosity and bulk viscosity is equal to 0 when the expanding rate large enough and the expanding configuration is the same result as the isotropic. And the way we prove it is very simple, as in that except that we have an additional equation for temperature. And the temperature equation is really bad in the sense that even the L2 estimate, you get a growth on the right side. And to tackle that, we're using the same technique, using the time weight to kill it off, and we hopefully eventually using the otherwise estimate to cover the smallness of the derivations. And this is to show the crazy things, and it's matching the variable, and this is one particular choose or derivative that works. Thank you for your patience.
Okay, so yeah, any questions?
Is it is it only one D, or do you think one can do something like it? Even in the equation where you put the variable x, this x was coming from the spherical symmetry. So
Yes, it's spherical symmetry. Unfortunately, we can only do spherical symmetry for the moment. The main reason is that the self-gravity in radial symmetry case, it can be represented by integral. Here, the self-gravity in the radial symmetry case is relatively simple. So if you have like, if it is not spherical symmetry, there's no symmetry at all. This is the inverse of the Laplacians, and it's not even in the same. Our study mainly are done in the Lagrangian code. So now how you deal with and this inverse Laplacian is in the Eulerian. So that means our technique can be strong. And we cannot, which means that you cannot check the flow map to study the self-gravity if it is not self-symmetry. If it's not spherical symmetry. And we don't have enough techniques.
even the local existence.
Yeah, even the local existence. I think someone had done it without this self-gravity. You can do it, but with the self-gravity. The main reason is that we don't know how to check the density profile across the mountain when you let the flow freely without symmetry. But I'm guessing if the gravity is not self-gravity, if the gravity is given by the Earth, is pointing downwards, then it's like something like that. The gravity is this way, probably something down. I've done some linear analysis about it, but I haven't figured out exactly how to do it. Yeah, my conjecture is that this one could be working, but the analysis I have done so far means showing me that at least with constant viscosity, maybe with degenerate viscosity, which you can bring up the BD entropy structure, probably it will work. BD entropy is the flash that structure for the probably they will work. I haven't figured out actually.
At some point you said you had infinitely many solutions up to a choice of constant.
Yeah.
Is there any natural way to select I mean, like you solve Poisson's equation on the torus, there's infinitely many solutions.
Yeah.
But your natural solution is the mean free one.
Right.
Is there any analog here?
We don't have that. Because for mass, we have conservation of mass.
Right.
Here, the temperature again, I think it's not really very conservative for the equations. It's a balance. So you have more mass, you can have one larger domain. So you can have larger generation of heat to balance it out. So we don't really have to select it. Select the bottom. Okay. Solution. Actually, I would say this is maybe a little bit controversial. I think the result we show is not. It's really showing that the model we given for the thermodynamic model is not good enough. Because imagine if a star really explaining configuration, it's a magnetic box.
Yeah.
And it's not really true. So which means that it's too simple. That's the only mistake.
Do you have an idea of what feature is missing from the model that would?
I know the feature because this is really a simplified model from the Tranjeska's books. I tried it. The other one, and we put out the equations. So the main reason is in the thermodynamic. So it's if you write it back to Fourier law, it's divergent of kappa when theta is equal to epsilon log. And in reality, this one kappa depends on log and theta, and epsilon also have to depend on log and theta. Okay. One particular choice is that the kappa have two proportions to if I remember correctly, it's proportion to log and log theta to the -1. Something like that. Or it's the other way. Namely, mean that you think of detect conductivity as a particle are throwing energy. They're playing catch, throw and catch.
But where the density is low, there should be less conductivity.
But it means that I think it's the other way around. It's positive and negative. No, it is. It's positive. So what is positively proportional to low? Namely, you have more particle to throw away things.
Yeah.
And if you have higher temperature, then the particle itself is vibrated harder. So it's harder to accept energy. So it's blocking the conductivity. That's the explanations. And they have a specific index for it from the book. And I tried it. I can only find the equilibrium in the case of radio signature. I don't know how to do the argument that you can reduce it to isentropic model. Do the thing. So I cannot prove it's spherical symmetry, but I can prove it in spherical symmetry case, basis solutions. Same goal as the layers. And this one would not give you infinity magnitude, at least in spherical symmetry case. Of course, it's more realistic model, but we don't know how to do this. And also another thing is the pressure. Now I only take it as K log theta. In reality, the pressure should be decomposed into 3 parts. One is some constant, the log gamma, same gamma as before. And we have the K log theta, and we also have the theta to the power 4. Power 4, I don't know, over 3 or 4. So this corresponds to 3 different mechanisms of supporting the gaseous star. One is coming from the electron, one is from the ion, one from the proton. So it really depends on what stage the star is. Each one of them has different effect. For electron star, this one is here, and for neutron star, no, in neutron star, this one is here. The neutron star mainly supported by electrons. But indicating further, white dwarf or something different for carbons. But in general, this is a middle part. Yeah, this is more realistic model from James' book. I don't know how to
There are no more questions, and everyone's welcome to join for lunch. We're going to go across the road to Churchill College and back here for our second speaker at 1 o'clock.